In this video, we're going to look at some of the features of the modulus of a complex number. Just a reminder, modulus is IB's way of saying absolute value. And so when we talk about the absolute value of a complex number, we want to know how far is that number from the origin, how far is that from 0. So they're saying consider the complex number z equals 3 plus 2i. So then we would graph that or draw that by going 3 in the real direction and then a positive 2 in the imaginary direction, and this is the, we can kind of relate these to vectors, so that's the vector that represents 3 plus 2i. So then when we find its modulus, we're just doing Pythagorean theorem again, and our work looks something like this down here. So we have 3 squared plus 2 squared to find the length of that hypotenuse in the root 13. Now the cool thing that I wanted to show you is when I go say 3 minus 2i, well, if you were to extend this graph, we would be coming down to here, and so it would be the point down there somewhere. So you'd have 3 minus 2i would end you in the fourth quadrant, but it has the exact same information here because when we square that negative 2, we get positive 4, just like when we square positive 2, like right here. So the cool thing that we wanted to that we can see in this example, and it becomes true for all situations, is that the modulus of z will be equal to the modulus of z star. Okay, so and then actually notice over here, well then they went in the negative 3 and the negative 2, so they have the same sort of this vector here is the same in any, put it in any quadrant, pretend I can draw, and it's going to have the same magnitude. It's going to have the modulus will be the same. So there's several values that will work for. But the important thing for us at this point is this information here. The next thing that they ask us to do is they're asking us to prove that if I have two complex numbers and I multiply those two complex numbers and then take their modulus, that's equal to the modulus of one times the modulus of the other. So what they did is they said, okay, well, let's let z1 equal a plus bi and z2 c plus di. And then when they FOIL that out, we get something like this. Notice the real and the real, and then when I take bi times di, that gives me b di squared. Let me write that right in here. When I do this, that gets me b d times I squared. Well, and as you remember, I squared is negative 1, and so that's how we get this negative sign right in here. And this is the real part. And then when you go this and this, that's how you get the imaginary parts that show up here. Okay, so then if we want the modulus of that, well, we just take each of those, the real part and square it, and the imaginary part and square it, and that's what shows up right here. So then they FOILed it out. You'll notice this part here came from the real part squared, and this part here came from the imaginary part squared. So then they noticed we lost our middle terms here, and then they factored out, what did they do? They regrouped, and so they said we have an a squared here and an a squared here. So they regrouped those and factored it out so that we had a squared times c squared plus d squared. And then we used these two terms right here and here, factored out a b squared. And so then we're taking this information and we're factoring by grouping. So then we had a c squared plus d and a c squared plus d, so then we could factor this way. Well, keep in mind with square roots, if you've got like square root of 4, well, that's easy, but times the square root of 9, I mean, that's 2 times 3 is 6, or you could say square root of 36, that's also 6. So you can put them together under one radical or separate it out like this. But this, you'll notice, is the modulus of z1, which came from right here, and this, you'll notice, is the modulus of z2.